All right, let's just dive right into this explainer and demystify matrices. If you've spent any time looking at advanced math or data science, you've definitely run into these imposing blocks of numbers, all neatly encased in those stark square brackets. Honestly, it's pretty easy to look at them and feel a bit intimidated. But today, we're going to change that. We're taking matrices from intimidating blocks of numbers to highly versatile, incredibly cool mathematical tools. So get your thinking cap on, because we're about to see how these structures form the literal foundation of modern computing. So here's a question to start us off. Are these things just rows and columns of data, or is there something more going on? Now, depending on the context, sure, you can absolutely think of a matrix as a simple data table. Maybe the rows are your different customers, and the columns represent their purchases. That makes sense. But as we're going to see, restricting our view of matrices to just spreadsheets means you're missing out on their true superpower. But check this out. When datasets get really massive, we can actually visualize matrices as pseudo-colored images to spot larger patterns. Think about it. When a matrix contains billions of elements, printing it out on paper is literally impossible. So instead, the numerical value of each element maps onto a color or a grayscale value in an image. Suddenly, a giant, incomprehensible grid of numbers becomes a visual heat map where we can actively see the data structures, the background noise, and the hidden relationships. It's a real game changer.
Here's our game plan for today. We'll start by meeting the matrix. Then we'll check out some special matrix families, dive into intuitive matrix math, tackle standard matrix multiplication, explore geometric transformations, and wrap up with the transpose operation and a cool trick called live evil.
Let's kick things off with Section 1, Special Matrix Families, or as I like to think of them, our cast of characters. Just like in any good story, there's a recurring cast of characters you really need to know. First things first, we gotta know their size. We usually light this out using an m rows by n columns convention. We simply call this the matrix's shape. And this is absolutely crucial because, as we'll learn in just a minute, this shape dictates exactly how different matrices can interact with one another. If a matrix has the exact same number of rows as columns, we call it a square matrix. If it has different numbers of rows and columns, it's rectangular, either tall or wide. Being able to spot the unique patterns inside these square matrices makes complex linear algebra so much less daunting. Take the identity matrix, for example. It has ones running right down the diagonal and zeros everywhere else, meaning it acts exactly like the number 1 in standard math. Then you have the diagonal matrix, where only that top left to bottom right line holds non-zero values. And then there are triangular matrices, where all the non-zero numbers are bunched up entirely above or entirely below that main diagonal line. Moving right along to Section 2, Intuitive Matrix Math, where we look at element-by-element operations. I call this math intuitive because, honestly, it mostly operates exactly how your brain assumes it should. Let's look at the clear distinction here. If you want to scale up a matrix, you use scalar multiplication, meaning you just take a single number and multiply every single element inside the matrix by that one number. Super simple. But what if you want to multiply two matrices together? Well, the intuitive way is Hadamard multiplication. You just pair up the matching individual elements from two identical-sized matrices and multiply them. Top left element multiplies the top left element, and so on. There's also this neat trick called shifting a matrix. Technically, in pure linear algebra, you can't just take a single number and add it to a whole matrix. But you can add a scalar multiplied identity matrix. Because the identity matrix is mostly zeros with ones on the diagonal, doing this only adds your number to the diagonal elements, leaving the rest of the matrix completely untouched. It's an incredibly powerful trick, used heavily in machine learning and deep learning to stabilize models. Which brings us to Section 3, Standard Matrix Multiplication, affectionately known as the unintuitive boss. All right, buckle up because we are leveling up to the much less intuitive way to multiply matrices. Forget the simple element-by-element stuff. Standard matrix multiplication operates completely differently, yet it's the absolute bedrock of modern computing. The most important thing to remember here is the golden rule of multiplication validity. You can only multiply two matrices together if their inner dimensions are perfectly concordant. What does that actually mean? It means the number of columns in your left matrix must exactly equal the number of rows in your right matrix. If they don't match, the math literally doesn't work. Imagine you have an m by n matrix multiplying an n by k matrix. Because those inner numbers, the n's, match up perfectly, we have a green light. And here is where the real magic happens. The size of your brand new product matrix is defined by those outer dimensions.
So an m by n multiplied by an n by k creates a brand new m by k matrix. Honestly, if you can just memorize this rule, it will save you so much headache down the road.
But how do we actually do the math? Well, instead of just multiplying the corresponding elements, we are actually calculating a systematic collection of dot products. To find just one single element in your new product matrix, you have to map a full row from the first matrix to a full column of the second matrix, multiply those pairs, and add them all up. If that sounds a little abstract, just try mimicking the motion with your hands. Literally hold them up right now. Move your left index finger horizontally across a row while simultaneously moving your right index finger vertically down a column. Multiply the numbers you point at and sum them together. That single resulting number represents just one coordinate in your new matrix. It's like this beautiful, intricate dance of data. Next up, Section 4, Geometric Transformations. This is where we see matrices in action.
This is where things get genuinely incredible. This is where matrices stop being static spreadsheets and start actively moving things around. Think of a vector as a geometric line drawn out in space. When you multiply a matrix by that vector, the matrix acts as a mathematical engine. Depending on the exact numbers inside the matrix, it can stretch that vector line, squish it down, or even rotate it to point in a completely different direction. It's fascinating to see this engine at work. In some scenarios, an original vector gets both rotated and stretched by the matrix engine. But in other cases, with a different vector, applying that exact same matrix engine might just stretch the line straight out without rotating it at all. When a vector only stretches and doesn't change its direction under a specific matrix, we call it an eigenvector. It's a very special phenomenon and a fundamental property of that specific matrix.
Finally, Section 5, Transpose and Live Evil, where we literally flip the script. For our final operations today, let's explore what happens when we start flipping matrices around. Sometimes, just to make the math work, we need to change the orientation of our data completely. The operation we use to do this is called a transpose, and you'll usually see it indicated by a little superscript T. Transposing is beautifully simple. You just swap the rows in the columns. So the first row of your original matrix becomes the first column of your new one. It essentially mirrors the data across the diagonal, easily turning a tall matrix into a wide one. But here is the real trick when you're dealing with multiplied matrices. If you multiply several matrices together, let's say we call them L, I, V, and E, and then you transpose that final result, how does that relate to the individual pieces? Well, the live evil rule shows us. The transpose of multiplied matrices equals the individual matrices transposed but multiplied in reverse order. So the transpose of L times I times V times E equals E transpose times V transpose times I transpose times L transpose. Live becomes evil. It's a bit quirky for sure, but it's an incredibly useful mnemonic. All this flipping action leads us directly to symmetric matrices. These are square matrices with a very special property. They are perfectly mirrored across their main diagonal. This means that if you perform a transpose operation, if you swap every single row for every single column, absolutely nothing changes. The matrix equals its own transpose. Because of this, they are highly numerically stable and an absolute dream to work with in computer algorithms. But you might be wondering, what if your data isn't naturally symmetric? Well, you can actually force symmetry. By multiplying any non-square matrix by its own transpose, an operation written as A transpose times A, you mathematically guarantee that the resulting product matrix will be perfectly square and perfectly symmetric. This little trick is a foundational step in so many advanced statistical algorithms, like principal components analysis and regressions. Let's lock all of this in. We've seen that matrices are way, way more than just basic spreadsheets. They can be full visual maps of data. They interact through strict dimensional rules where those inner numbers absolutely have to match. They act as actual mathematical engines for geometric transformation, stretching and rotating space itself. And their properties can be manipulated and reversed using operations like transpositions and rules like live evil. I want to leave you with this one thought to ponder. Throughout this explainer, we've mostly been looking at tiny grids and simple 2D lines. But what happens when you scale this up? If we can easily visualize these stretches and rotations in 2 dimensions, just try to imagine the unimaginable shapes and geometric contortions that artificial intelligence models are twisting your data into, operating across literally billions of dimensions right now. It is all the exact same math, just on a massive, mind-bending scale. Thanks so much for joining me on this explainer.